So anybody who will help me what we have taken last time? Is screen visible? Okay.
Yes, sir, visible.
So last time I think I have started the steam turbine chapter. So basically everybody know what is steam turbine. What is steam turbine? Who will define? Anybody of you? Anybody of you? Okay, am I audible?
Yes, sir.
Okay, screen visible?
Yes, sir.
Is screen visible?
Yes, sir.
Kunal,
Yes, sir, visible.
uh, title screen is visible, na?
Yes, sir.
Steam turbine,
Title
hello,
screen.
hello. Steam turbine, steam turbines is visible. That first PPT named as steam turbines.
No, sir. Title.
No, sir. Folder file is visible.
Oh, okay. Now I think steam turbine that screen is visible. Okay. I think visible. Hmm? So steam turbines was started last time. So anybody of you can define steam turbine? Anybody of you will define steam turbine? Kunal. So in
Yes, sir.
short, we will go for revision. So steam turbine is a device which converts kinetic energy of steam into mechanical work. And for this, here nozzles are used. So first of all, nozzles are the inbuilt device in the steam turbine, which will convert the thermal energy of steam coming from boiler into kinetic energy. And that increased kinetic energy steam is impacted on the blades of steam turbine. Okay, and executed the work. Okay, so last time we have started, though we know that steam turbines are used for power generation. Another purpose of steam turbine is power transport. Okay. Then steam turbine already we defined. It is a prime mover in which the potential energy of the steam is transferred into kinetic energy, and later okay, the steam turbine is a prime mover in which the potential energy of the steam is transferred into kinetic energy, and Power transport. Yes, yes. Ah. Uh, has been review of it is review na reuse if you get reuse power gains. Okay. So classification of steam turbines. Steam turbines are mainly classified into two categories. One is impulse turbine and another is reaction turbine. Now, which screen is visible on your screen? I am not getting. I am come here. Well, on my screen, power applications of steam turbine that screen is visible here. On which your screen, which screen is displaying? Anybody?
Sir, a classification of steam turbine is visible.
Okay, take it. What? Why it is happening? I don't know. Now which screen is visible? Screen is visible.
Yes.
Okay. So steam turbine was started. Okay. So steam turbine was started. Then classification is that there are two types of steam turbine. One is impulse turbine, another is reaction turbine. In the impulse turbine, what happens? So of the impulse is going to be generated at once only. So there are nozzle is there, and in the steam expansion of that steam takes place only in nozzle. Afterwards, there expand the pressure of that steam remains constant. Okay. So that kind of steam turbine we call it as a air impulse kind of steam turbine. Another kind of steam turbine is reaction type steam turbine. Okay, where in that steam turbine, here expansion of steam is partially taking place during the stages, or continuously the expansion of steam takes place during the stages. So there are two types of blades we know, moving blades and fixed blades. So expansion of steam taking place not only in nozzle but also in fixed blade, not, and also in moving blades. So there are this kind of two turbines are there. Again, we have also discussed about the different another basis of classification of steam turbine. One of that basis is depending on the uh, here depending on that pressure, how the steam turbines are classified. Anybody of you, how we start here? Anybody of you? Am I audible? Which screen is available? Visible? Kunal?
Sir, folder.
Folder only. I don't
Yes,
know
sir.
what is problem. Just wait for 2 minutes, 5 minutes. I will. Okay. Now applications of steam turbines are available. Kunal, Kunal,
Now audible, sir.
huh?
Yes,
Visible,
sir.
sir.
Yes, sir.
Applications of steam turbines is visible.
Yes, sir.
Okay. Okay. Now it's settled. Sorry for the inconvenience. Okay. So classification of steam turbines, we have discussed about the classification. Impulse turbine is there. Another type of turbine is reaction turbine. And impulse turbine, we know that the steam expands only in nozzle. Okay, that is fixed nozzle. And afterwards, the pressure of that turbine remains, pressure of steam in the turbine remain constant. So that type of turbine we call it as a impulse turbine. Now another type of turbine is reaction turbine, in which the steam expands both in fixed blades or fixed nozzle as well as moving blades. Then combination is there. Sometimes we are going to use the impulse turbine as well as reaction turbine. Then according to number of shafts, single shaft, multi shaft turbine. Okay. Then according to method of governing, turbines with throttle governing, turbines with nozzle governing, turbines with bypass governing. So these are the types of turbines according to the number of shafts. Okay. Then afterwards, single shaft turbine, multi shaft turbines with throttle governing, turbines with nozzle governing, turbines with bypass governing. Then depending on the how the steam is extracting or it's here exhausting the heat. Okay, depending on that, condensing turbines with generators means the turbines which are using condenser, like our cycle, vapor power cycle. After steam turbine, we are passing the steam to the steam condenser, where steam get condensed. And we know condenser types, that two types of surface condensers, jet condenser and surface condenser. So that kind of turbines are condensing turbines with generator. Then condensing turbines with one or more intermediate stage extractions. Sometimes all amount of steam cannot be condensed. Some amount of steam is going to be extracted and it given to a particular application. So for that application, whatever pressure is suitable, so for that pressure steam is sent to that particular application. Then back pressure turbine, topping turbines. Okay. Then low according to pressure, low pressure turbines, medium pressure and high pressure turbines. So low pressure means those are generating this pressure, those are having pressure 1.2 atmosphere to 2 atmosphere. Okay, the medium pressure up to 40 atmosphere and high pressure turbines more than 40 atmosphere. And very high pressure turbines, they are having pressure near about one more than 170 atmosphere, and supercritical turbines having pressure 225 atmosphere and higher. Okay, so this advantage of steam turbines over steam engines, that they we have recovered. So thermal efficiency is higher because losses are less as compared to engines in case of turbines. Okay, and in the steam engines, reciprocating parts are there. Therefore, balancing problem is there, vibration problem is there. But in case of the steam turbines, all parts are rotary parts are there, and therefore we cannot face that much balancing problem or vibration problem. Then higher and greater range of speed is available. And in steam engines, as the here reciprocating parts are there, we are having limitations about the speed. But in case of the here steam turbines, as the rotary parts are there, therefore we are getting higher and greater speed is available. And lubrication is much more easy. Power generation is uniform. Okay, steam consumption is less. So these are the advantages of steam turbines or steam engines we have taken. Then afterwards, we have discussed about the difference between impulse turbine and reaction turbine. Then the impulse turbine and reaction turbine, we know the steam completely expands in the nozzle in the impulse turbine, and its pressure remains constant during its flow through the blade passages. And the reaction turbine, the steam expands partially in the nozzle, and further expansion takes place in the rotor blades. The relative velocity of steam passing over the blade remains constant in the absence of friction. If the friction is not there, then remaining velocity is remaining constant. And the relative velocity of steam passing over the blades increases as the steam expands while over the blades. Means as pressure is going to be expanding, therefore here velocity is also goes on here increasing. Okay, and here it is remaining constant if friction is not there. Blades are symmetrical in case of impulse turbine, and here blades are asymmetrical in case of reaction turbine, because we have to create the area variation during the passage for the reaction turbine, because as pressure is goes on decreasing throughout the stages. Okay, and for the same power developed, as pressure drop is more, number of stages required are less. Then blade efficiency curve is flat in case of the impulse turbine. Reaction turbine, the blade efficiency curve is more flat. Okay, less flat and more flat. Then steam velocity is very high, and therefore steam velocity is very high. The blade efficiency curve is more flat. The steam velocity is very high, and therefore compounding of turbine is necessary in case of the impulse turbine. Okay, the steam velocity is not very high, therefore speed of turbine is less, and compounding is not necessary in case of the reaction turbine. Okay, then we have discussed about here impulse turbine, reaction turbine. These are only one's row is there, this is going to be nozzle is there. Okay, and these are the moving blades. Okay, so steam is here pressure, here steam pressure is decreasing only in nozzle. So this is nozzle section, nozzle pressure is decreasing. Okay, arrow I am showing here, and afterwards the pressure remaining constant. So I am here using arrow. Then afterwards, during nozzle, velocity of steam increases. Okay, and when the steam strikes on the moving blade, it exchanges its velocity to the blade, and blade velocity will increase, and steam velocity will goes on decreasing. So what happens in the nozzle? Steam pressure decreases and steam velocity increases. Afterwards, in impulse turbine only, the pressure remains constant. Pressure curve is going to be straight one. It is not going to be changing one. Then, but velocity is going to be increasing in the nozzle. But when it strikes on the moving blade, it will give the momentum to the moving blade. Therefore, moving blades will move, and its velocity, its own velocity, will go on decreasing. So this is going to be the pressure and velocity curve for the impulse turbine. After reaction turbine, there is going to be nozzle. Blades are symmetrical. We are knowing here, and asymmetrical blades, aerofoil shaped blades are there for the reaction turbine. So here nozzle, fixed blades are acting as a nozzle. Okay, and here moving blades, as asymmetrical shape is there. There is passage is there through it means the as area at the outlet side area goes on decreasing. Therefore, pressure is goes on decreasing. Expansion of that steam is taking place continuously, and as expansion is taking place, velocity also goes on. Here, here velocity increases during the expansion, but here when the steam is flowing through on the moving blades, here velocity of that stream is goes on decreasing. So moving blades of reaction turbine, what happen? Moving blades of reaction turbine, pressure also decreases, velocity goes on decreasing, and fixed blade are acting as nozzle in case of reaction turbine, where pressure is goes on decreasing, but here velocity goes on increasing. रिॲक्शन टर्बाईनच्या फिक्स्ड ब्लेडला काय असतं, तर नोझल इफेक्ट असतो. तर तिथं काय होईल, प्रेशर डिक्रीज होईल पण व्हेलॉसिटी काय होईल, वाढत जाईल. ओके, आणि मुव्हिंग ब्लेडला प्रेशर पण डिक्रीज होईल आणि व्हेलॉसिटी पण डिक्रीज होईल. दॅट इज द कन्सेप्ट ऑफ रिॲक्शन टर्बाईन. Okay, so then construction of a, we have seen afterwards. Just a minute, I will. Hello, 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 hello. लेक्चर चालू माझं. So impulse turbine, impulse turbine also we have seen impulse turbine. And afterwards we have seen the uh, compounding of steam turbine. Then what is compounding of steam turbine? Anybody of you? Can define compounding of steam turbine. Anybody of you compounding of steam turbine can define? Because this is revision, because this chapter is very theoretical and only 1 2 hours analysis part is there. Anybody of you, please unmute and tell what is compounding. At least you tell what is meant by compounding. Anybody of you compounding? Compounding of steam turbine. Anybody of you? Okay. So okay. Steam turbine compounding. This I think I have shown on that day to you. Turbine casing rotor. So on for the casing, okay, or it is called a stator. It is not moving part. So fixed blades or nozzle is attached to this particular casing, okay, and moving blades are attached to the rotor. So this is a turbine rotor where moving blades are attached. So in between two moving blades, always there is a row of fixed blade. Okay, then impulse turbine blades are symmetrical, while reaction turbine blades are asymmetrical. So here it is impulse turbine blade, it's the reaction turbine blade. Then blade shaped are symmetrical in impulse turbine. And here we have gone through this diagram already. In impulse turbine, pressure drop, nozzles and not in moving blade. Classification, direction, radial flow, tangential flow, axial flow, how the steam is flowing into the impeller of that turbine. Based on stages, single stage, multi-stage. If all the assemblies are connected in only one stage, all the cylinders are mounted in only one stage, or all the blades, moving blades, fixed blade nozzle are connected in only one cylinder, then it is called a single stage. Then if the two stages are used, if two cylinders are used, then it is called as two or more cylinders are used, then it is called as multi-stage. Okay, then compounding. Now here these difficulties associated with the only compounding is done for the impulse turbine, not with the reaction turbine. So compounding means what? The reduction. We have to reduce the speed of that particular turbine to a practical limit. Okay, so that is called as what? Compounding of steam turbine. Okay, then there are two types, how we are absorbing the energy. Depending on that, there are three types of compounding method. One is velocity compounding, another is pressure compounding, and third one is what? Combination pressure and velocity compounding. So what happens in the velocity compounding? Anybody of you? Velocity compounding. So here in the velocity compounding, the velocity of the steam is absorbed during the stages, or we are increasing the number of stages for the impulse turbine. As we know that for impulse turbine there is only one stage, nozzle and moving blade. So we are increasing the number of stages. Number of stages means we are increasing the blades, number of moving blades or fixed blade. So here by increasing the number of blades, fixed blades in the series arrangement, so we are absorbing the velocity of the steam throughout the stages. So what happens? And this is a nozzle sectional view. Okay. After when the steam is expanded in the nozzle, its pressure is goes on decreasing and velocity goes on increasing. Afterwards, it as it compounding is only done for impulse turbine. Therefore, pressure is always remaining constant in the case of the impulse turbine. And then fixed blade, what is there, they are acting as only this is moving blade. Okay, first set is moving blade. After nozzle the steam is impacted on the moving blade, pressure is remaining constant, but steam will exchange its momentum to the blade, therefore its velocity will go on decreasing. Okay, and here velocity of blade will increase but velocity of steam will decrease. Fixed blade are acting as a guide blades in case of impulse turbine. There are only the purpose is only to guide the steam or to the next set of moving blade. So this is going to be moving blade. Okay, concave surface. Okay, and this is moving blade. The afterwards velocity pressure is remaining constant. Velocity goes on decreasing. So by increasing the number of moving blades rows, here velocities of that particular stages, velocity of steam during the stages is continuously decreases. So that type of compounding method is called as velocity compounding. So these diagrams you have to make practice. Then they have given explanation. There is only one set of nozzle and two more rows of moving blades. There is a row of fixed guide blades between moving blades. So in between two, or we can say shortly, roughly, in between the two moving blades, fixed blade, one moving blade is there. Then one guide blade is there. Then kinetic energy of the steam is absorbed during the moving blades only. An example is Curtis turbine. Okay. Then afterwards pressure compounding. Pressure compounding is what? We have to absorb the pressure. And we know that what will happen only in the nozzle of impulse turbine pressure is goes on decreasing. So what we are doing is so we are increasing or we are here fixed blades we are introducing. So this is nozzle, moving blade, fixed blade, moving blade. So in between the two moving blades, one set of moving fixed blade is arranged, and that we are arranging so that it will act as a nozzle. Okay, so what happens here? Pressure should get on decreasing. So here nozzle, the pressure is goes on decreasing. Okay, velocity is goes on increasing. Okay, afterwards in the moving blade, velocity is goes on decreasing. So dark curve is there of the velocity and dotted curve is there of the pressure. So afterwards pressure is goes on, pressure will remain constant to the moving blades. Okay, because it is impulse turbine. Okay, when nozzle will come, then and then only pressure will goes on decreasing and velocity will goes on increasing. So here dotted line will start here. Pressure here dotted line. Pressure is goes on decreasing. Afterwards moving blade it is remaining constant. It is fixed blade acting as a nozzle. Pressure goes on decreasing. Okay, and afterwards it is remaining constant. So this is going to be this kind of curve is there. It is going to be of the for pressure. Then afterwards velocity is increasing in the nozzle. Okay, but when it is strikes on the moving blade, momentum exchange takes place and its velocity goes on decreasing. Afterwards, these are the passages. The two lines are the vertical lines are there. In between, whatever the space is there, that is called as passage. And during the passage, velocity as well as what pressure is remaining constant. Okay, and here throughout the pressure means by increasing the number of fixed blade, the pressure of that particular steam means fixed blade is acting as nozzle. Okay, and here pressure is going to be absorbed of that steam throughout the stages, and when suitable pressure at suitable pressure or suitable velocity the output we are getting, so at that time we are stopping this compounding stages. And another type of method, compounding method is there. It is pressure velocity compounding. Now both combination we have used. So here it is going to be nozzle, then moving blade, fixed blade. Means two bit in between whatever the combination is there. We are increasing nozzle and we are increasing also fixed blade in the combination, moving blades in the combination. So this is nozzle. Okay. Afterwards moving blade, then followed by the row of fixed blade, again followed by row of moving blade. Means in between two moving blades one fixed blade is there, or in between two fixed blade we can say one moving blade is there. Okay, so depending on stages. So moving blade, fixed blade, moving blade, then nozzle. So what will happen in the moving blade, fixed moving blade, the velocity of that steam is goes on continuously decreasing, and throughout the nozzle the pressure is goes on decreasing. So where the fixed blades are there or nozzles are there, pressure is goes on decreasing, and throughout the moving blade the velocity is goes on decreasing, and continuously the pressure during the stages, pressure as well as velocity is going to be absorbed. So that type of method is called as pressure velocity compounding. So this is going to be required for what purpose? Because here we have to see that here we have to see that your velocity at the outlet shaft or output shaft should be at the for the practical limit. Okay, so now this is going to be velocity diagrams are there. Okay, so this is very much important part. Okay, everybody is listening. Okay, up to revision anybody having problem? If not there, put yes and we'll so that we'll continue. I have taken revision for because so that it is very theory part is very important and little bit complicated or lengthy. So diagrams you have to make practice. If you are having if no problem, then write down here. Can I continue to next? Why? Yes, Kunal is why. No problem, Nikhil. Okay. Only two are having. Two have given only say here. Okay, Suhas. Okay, Saurav. Why? I have to continue. Okay. Now here it is going to be velocity diagrams or velocity triangles. These are very much important concept now. Here now concentrate. I request everybody to concentrate. Okay. So this is going to be blade, whatever section because we have less here. This is going to be blade hatched line. So this blade is moving with velocity u. The blade is moving with velocity u. So now some books they have written given notation for the steam velocity components. There are now we are using the various steam velocity components. So C is going to be steam velocity component by some books they have used. But here many books also have used for the steam velocity as a V component. Means but blade velocity everybody has used everybody have used U as a velocity component. But for steam velocity components, somebody have started V and somebody have started C. Okay, so we'll don't confuse in that. So VW1 in some books it may be CW1. In this is here VR1. Some books it will maybe CR1. Here it is going to be VA1. Okay, V axial. Okay, or VW1. Here it is going to be VF1. Okay, there it should be CF1. Okay, so it's like that. V can be replaced by C in some books. Okay, now here there are this is going to be blade, and this blade is going to be common for when the steam is entering at the blade. Okay, at which tip or which edge, so that side is called as inlet of that blade, and where the steam leaves the blade is called as outlet of that blade. Okay, now if you, there are going to be different components of that particular steam. Okay, so this blade is moving with velocity u. Okay, it is common for both inlet velocity triangle as well as what outlet velocity triangle. So here it is going to be nozzle. So from that nozzle, here it is going to be V1. Okay, from this nozzle. So okay, let it be so that we will not confuse. Mhm. Okay. So I think I was out of the meeting for some time. Sorry. For today, I think. Not getting. Okay. Now I think I am getting. So this is screen visible. Kunal,
Yes, sir.
screen visible.
Visible, sir.
Okay. Because that. Okay. So this is going to be blade. I wanted to show that nozzle how the steam is impacted on the blades. We'll see this. Okay. Really did we? Now here this is a VA1 that we are considered as a C1, okay, or V1, okay. So this is the velocity the from the nozzle. Here is one nozzle is there, and from this nozzle the steam is flowing in the tangential direction to the tip of the blade, and that velocity component we call it as a V1. It is the resultant velocity component coming from that particular nozzle, and this velocity component is having two components, and this velocity makes an angle alpha 1 with the nozzle, with the horizontal, and that is called as nozzle angle at inlet, because this velocity component is coming from that nozzle. We can va1 or we can call it as a v1, and this velocity component is making angle alpha 1 with the nozzle, okay, and this velocity is having two components. One is horizontal component, it is called as VW1. If you see V1, if you resolve, it is having two components. One is V1, okay, VW1. Another is what? VF1. So VF1 is the vertical component, and VW1 is called as horizontal component, or it is also called as whirl component of steam at inlet. Whirl component of steam at inlet, and this component is responsible. Horizontal component of that V1 or VA1 is responsible to make the whirling action of that particular blade, or to rotate that blade. Which component is responsible? VW1. And VF1 is what? Whatever the steam is there, to make its flow from inlet to outlet, to glide the steam over this particular blade. So this VF1 component is responsible. So it is called as flow component of inlet. VF1 is what? Flow component of inlet. VW1 is whirl component of steam at inlet, and it is means it is horizontal component of V1, and where VF1 is vertical component of here, vertical component of this V1, VA1 or V1. Okay, and whatever the angle, this is going to be angle is there, alpha 1, it is going to be angle made by the here resultant component V1 or VA1 with horizontal. Then this on this same diagram, okay, we can locate our blade velocity, which is moving with velocity u. Here u1 and u2 are going to be same, so u is going to be the blade velocity. This much is the component of u velocity, and here what are the remaining? Now there is u, and here it is going to be what? One is velocity of steam. So there is a relative difference in between these two components. One is what? Blade velocity component u1, and the steam velocity component v1. If you resolve, if you draw here, then in that case, this component is called as VR1. It is called as what? Relative velocity component of steam. Means generally it is the relative difference, relative speed difference between the steam and blade. So when the steam is impacted on the blades of the turbine, what happens? Blades are moving with very low velocity as compared to steam. So steam is here moving with very high velocity, and blades are moving with very, as compared to steam, less velocity. And whatever the difference is there in between their speed or velocity, it is called as relative velocity or relative difference. This is the difference between the two velocity component. It is called as relative speed. Okay, VR1. Okay, and whatever this VR1 is making angle with the horizontal, it is called as beta 1. It is called as beta 1, or it is called as blade angle at inlet. VR1, whatever the angle it is making with the horizontal, it is called as blade angle at inlet. Okay, so this is beta 1. Now this is alpha 1. Okay, and this is VA1 horizontal component is VW1, VF1. This is blade is moving with velocity u. Okay, this is u1 or is equal to u, or u is equal to u2. And similarly, when the steam is glided on that blade and leave this particular blade, then it is coming with one velocity component that is called as VA2. VA2, or we can call it as a V2. Again, at the outlet side, whatever the VA2 is making angle with the horizontal, it is called as alpha 2. It is called as blade angle at outlet. Okay, then the blade is moving with velocity u. It is common at inlet and outlet, so this is going to be u2. Okay, and this va2 and u2 means they are having what? Another difference. It is called as vr2. Okay, and this is going to be blade velocity, relative velocity component at outlet. So whatever the relative velocity component is making angle with horizontal, it is called as beta 2, or it is called as blade angle at outlet. Okay, and this va2 is also having two components. One is what? vw2, and another is what? vf2. Vf2 is making responsible for making the flow of the steam from inlet to outlet, inlet blade angle to, or inlet edge to the outlet edge. Okay, this vf1 and vf2, and this vw1 here and vw2 are responsible for the whirling action or work done of that particular steam of the turbine. Okay, so this va2 or v2 makes angle with horizontal is called alpha 2, or it is called as nozzle angle at outlet. So alpha is related for nozzle angle. 1, here we can say that one symbol is there, it is related to inlet, and two symbol, suffix 2, not symbol, suffix 2, suffix 1 is related to responsible for inlet parameters, and suffix 2 is respect here it is going to be specified for the outlet velocity triangle. So inlet velocity triangle is there and outlet. One means inlet and another two will be outlet. Everybody got at least nomenclature of this. It is little bit difficult to understand on online, but still okay. So nomenclature, what is V1 or VA1? It is the resultant velocity coming from. So next slide will go. It is nomenclature. Okay. Here it is going to be nomenclature. Beta 1 is the blade angle at inlet. Beta 2 will be blade angle at outlet. Another definition of blade angle at inlet will give in terms of VR1 and VR2. Anybody? VR beta 1 and beta 2 in terms of VR1 and VR2 will define. Okay, beta 1 and beta 2. Anybody of you? Beta 1 is what? It is the angle made by VR1 relative velocity component with the horizontal. And beta 2 will be anybody? Today I think nobody is concentrating. Beta 2 will be Kunal, Suhas, Kunal, Nikita Pawar. Okay. So okay, so I will not draw. I will go to our here sketching method. So beta 2 is going to be blade angle at outlet. U is a combined or tangential velocity of the blade with which that blade is rotating. VA1 or V1 we can say here in our diagram. V1 is absolute velocity of steam at inlet with moving blade. Okay. Then V2 is absolute velocity of steam at outlet. VW1 is what? Velocity of whirl at the exit. Okay, velocity of whirl at the exit moving blade, that is tangent velocity component. Okay, at inlet. VW is whirl component of steam at outlet, or it is a horizontal component of V2, VAW1 horizontal component of V1. VF1 is velocity of flow at the entry at or flow component of steam at inlet. VF2 flow component of steam at outlet, and VR1 relative velocity of steam, okay, at inlet. VR2 relative velocity of steam at outlet. MS is the mass of steam flowing over the blade, and D is the mean diameter of blade. So afterwards we'll go for it. So now we have to use the common diagram. So we know that velocity is common. U velocity is going to be common at inlet and outlet. So this is going to be U velocity. Whatever the U1 and U2 both are same because the blade is moving with only one velocity. But steam at entrance, these are velocity components are different. At inlet side, velocity components are different. At outlet, velocity components are different. Therefore, here in but the blade is moving for inlet triangle as well as what outlet triangle with the only constant velocity, that is u. It is called as blade velocity. Therefore, this common diagram. Common diagram means what? Blade velocity is taken common for both inlet triangle and outlet triangle. Now that we'll go for. But before that, I think I have to draw. I have to draw you. I have to help. Miss. I have to draw this diagram. Okay. So So I will try. I will now sketch. Okay, so that every but it will be okay. Now here is your screen visible? So let us we can say consider this kind of blade. So okay, this is the one blade. So the diagram everybody have to make practice of the diagram. This is going to be one blade. We are considering one. Okay, let us consider now this is going to be one blade. Okay. Now we are considering that the blade is moving with one tangential velocity. It is u. Here our notation will be u. Okay. Then the velocity from the nozzle. This is going to be considered this as a let's consider this as a nozzle. Okay. And from this one velocity component is result velocity is coming and it is impacting on the tip of that blade. This velocity we call it as anybody of you. आता एवढं आपण सांगितलं जरा थोडं इंटरॅक्शन पाहिजे अदरवाइज anybody of you. This velocity is called as v1 now, or we can say it as a c1. This velocity v1, what it is making with the horizontal, it is called as angle made by this here with the horizontal, that we called as a alpha 1. That we call as a alpha 1. And this v1, I told you, it is having two components. One is what? Vertical component we can say. It is called as vf1. It is called as flow velocity component vf1. Okay. And this v1 is having another component. It is called as horizontal component. This is v1 is the resultant velocity coming from the nozzle. Okay. It is having two components. One is v1 and another will be vw1. Okay. Now, but when this v1 velocity of that particular stream is there, at that time blade is moving with some velocity, that is u. Okay. If you write this blade velocity here, u. If you say here, this will be u. If you consider this as a blade velocity component, will be u because it is tangential direction, horizontal direction. Okay. And this nozzle angle, nozzle velocity is coming, making angle alpha 1 with this tangential direction. Okay. This is going to be u1. But v and u, v1 and u, there is one speed relative difference is there, and that we call it as a anybody of you message to this is called as relative velocity, that is called as vr1. Okay. And whatever this vr1 is making angle with the tangential direction, it is called as blade angle at inlet, or it is called as beta 1. So at this is the inlet side, this triangle, everything is called as what? This is called as what? Inlet velocity triangle. Inlet velocity triangle. Okay. Anybody having doubt about the inlet velocity triangle? Please ask. Otherwise, I will continue. Yes, you can write our usual practice. Yes, yes, yes. Afterwards, I will not draw neat diagram so that you can copy. Everybody understood? If yes, you can write yes message. Otherwise, whether shall I repeat? Okay, Nikita Power is telling that she understood. Yes. Okay, Shubham Gandole also is telling yes. Okay. Others reply. Again, I am going to repeat because this is very important and this is going to be basics. Okay. Now this is going to be another component. This is going to be at outlet. The velocity. This is going to be relative velocity. Okay. VR2 outlet side. Okay. Then there is going to be there will be u velocity. Velocity will be u. Okay. And whatever difference in between this u and VR2, that we called as a v2. Again this v2, whatever it angle making angle with the horizontal is called as vr2, whatever it is making angle with the horizontal is called as beta 2, and whatever this v2 is making angle with the horizontal is called as alpha 2. This v2 is also having two component now. One is vertical component at outlet, it is called as vf2, and one will be the horizontal component which is responsible for the work done, it is called as vw2. Okay, this v2 is also like v1. This v2 is also having two components. One is vertical, it is called as vf2, and horizontal is called as vw2. And whatever relative difference is there u and here, this will be vr2. This is called as here outlet velocity triangle. This is called as what? Outlet velocity triangle. Outlet velocity triangle. Okay, outlet velocity triangle. Anybody of you having a problem with this now? Because at least understood what is meant by VW1, what is meant by beta 1, what is meant by beta 2, what is meant by alpha 2. Alpha is related to nozzle, or it is called as nozzle angle at inlet alpha 1. Alpha 2 is nozzle angle at outlet. Anybody have objects, doubt, or say here not understanding? Because this is afterwards all the analysis part is depending on this triangle. Okay. Anybody yes or no? At least yes, yes, yes. But I will continue. Okay, so now I will go to our printed diagram. So this is because now I will come to again. So this is again, I will repeat again once again. Okay, this is going to be blade. Okay, it is moving with some constant velocity that we call as u1 or u2. Here it's going to be both are same, u1 or u2. Okay, okay. So here we are good. So here only v1. This we consider as a v1. This we consider as a v2 in our diagram. Only that changes there, v1 and v2. Okay, so this blade from this nozzle, this is going to be coming from the nozzle. Okay, from the nozzle, this v1 velocity is coming at the tip of that particular blade. The blade is moving with velocity u. Okay, you can consider u is equal to, here we can say in this diagram, u1 or not, if you are saying this as a u1 is equal to, or you can say if u is equal to u, here also is going to be, it will be u. Okay, both are same, u1 and u2. Okay, now here the blade velocity from that, this is a v1 resultant velocity coming from the nozzle. Okay, v1, it is impacting on the tip of the blade at the inlet side. Therefore all these parameters, okay, these are called as what, inlet velocity triangle. So whatever this this will be inlet triangle, and this will be outlet of a triangle. Okay, now here the steam is coming, impacting on this, coming from the nozzle at angle, and this nozzle is located at alpha 1 angle with the horizontal or tangential direction. This is called as alpha 1, this is called as v1. Okay, this v1 is having two components, v1 is having two components. Horizontal will be vw1. Okay, horizontal will be what, vw1, and vertical will be vf1. Okay, now here there will be, we can on the same tangential direction, this is tangential direction, we can locate our velocity u. Okay, from this into here in the direction, horizontal tangential direction. But we know that steam velocity is more than the velocity of blade, and therefore there is a relative difference in between u and v1, and that component, relative difference component, is called as vr1. And whatever this vr1 makes an angle with horizontal, it is called as beta 1, blade angle at inlet. Okay, similarly, now when the blade will, this steam will glide, we do the work, move the blade, and this steam will glide over this particular blade. This will glide over this particular blade. Don't draw in our diagram. Okay, and this will emerge in the form of v2. Okay, at the same time, blade will move in this direction with the velocity u, and there is v2 and u. There is a difference in velocity, that is called as vr2. Now, theoretically, we say that vr2, whatever this making angle, relative difference in between u and v2, and whatever this vr2 makes an angle with horizontal, it is called as beta 2. Okay, and whatever this v2 or v1 makes an angle with horizontal, alpha 1, like this v2 makes an angle with horizontal or tangential direction, it is called as alpha 2. Again, this v2 having two components, one is what, vertical vf1, and horizontal vw1. Vw1, well, these are called as vw1 and vw2. These are called as whirl component, and responsible for what, here, action or moving action of blade, or work done, moving action of. And vf1 and vf2 are flow component. They are responsible for making the flow of steam throughout the turbine or throughout the blades. There is vf1 and vf2. Now everybody understand nomenclature and diagram. I have repeated 3 times because this is very important. Anybody? Yes, if it is yes, understood, then write yes so that I can continue. I will ask you to draw the diagram. Nikita Paul is only saying yes. Others, if it is not, then ask me to repeat. Fast Nasti, yes. Okay, good. Gaurav, good. Saurabh Pawar, good. Okay. Now, okay. Now you draw the diagram because for the practice. Okay. Otherwise, okay. We'll here. Now we have to draw the combined diagram for this common diagram. Okay. Now common diagram for this. Now write down. So common diagram is there. Like now here. Velocity u is common for both. So here what we do, we have to draw the graphical method also. Velocity, this is a tangential velocity u is common for both triangle, inlet velocity triangle as well as what outlet velocity triangle. So from this we are now here considering nozzle. So this is going to be here. Let us consider that this is going to be the result velocity coming from the nozzle. Let us consider the V1, or some books it is given as C1. Whatever this angle made of this V1 with the horizontal, that we call it as a alpha 1. Okay. Then U and V1, there is one relative velocity. So this is, let us consider this is blade is moving with this velocity. Okay, U. Then U and V1, it is having here draw once again. So this is going to be U. So this will be straight line understand. This is alpha 1 blade angle at another angle at inlet, and from this the velocity v1 is coming. Okay. Now u and v1, there is going to be what relative difference, and that component if you join this v and v1, so this is a straight line consider, and this component we call it as a VR1 relative velocity component at inlet, and this is having, if it this is making angle, some angle with horizontal, and that angle is called as what beta 1, it is called as blade angle at inlet. Beta 1, it is blade angle at inlet. Now this V1 is having two components, one is vertical component. Here if you draw this vertical line here, if you join this, okay, so this component is called as vertical component of VA1 is called as VF1. This is flow component of steam at inlet, and this will be horizontal component. V1's horizontal component is called as what VW1. So this is going to be the inlet velocity triangle, neglecting that blade section. So this is U velocity, blade velocity in tangential direction U. This is the nozzle angle, nozzle located at angle alpha 1. It is called as nozzle angle at outlet. Okay. Then the velocity from that nozzle, result velocity of steam coming from that nozzle will be V1. Okay. And this V1 is having two components. One is VF1 vertical and VW1 horizontal. And U and V1, there is relative difference. And that component, if we join this U and the end of U and end of V1, that component is called as VR1. Okay. Emerging now from this only, another relative component will emerge. That is called as VR2. This is called as what VR2. Okay. And whatever this VR2 makes an angle with the horizontal, it is called as beta 2. It is called as blade angle at outlet. Now here also this U and VR2, there is one relative difference. I mean this U and VR2, like this VR1 and V1, VR1 and U, there is relative difference that we called as a V1 and U, relative difference we called as a VR1. Similarly VR1 and U, VR2 and U, relative difference will be differently called as V2. This will be what V2, and this V2 is having two components again. One is what here horizontal component and vertical component. If V2 if you resolve into two components, it is having two components. It is having two components. One is what VF2, vertical component of V2 will be VF2, and horizontal component of V2. This is V2. Okay, this will be V2. Okay, I will. Okay, this is V2, this is VF2, and horizontal component of V2 will be this. I will draw it as a VW2, vertical component of team at outlet. Okay, and this is whatever the V2 makes an angle with the horizontal is called as alpha 2. It is nozzle angle at outlet. So this is called as combination of velocity triangle, combination of inlet and outlet velocity triangle. It is called as combination of inlet and outlet velocity triangle, or common blade velocity triangle. It is blade velocity is taken common for both because it is remaining constant irrespective of inlet speed or irrespective of the outlet velocity triangle. Inlet or outlet velocity triangle. This U is remaining constant. Therefore, this is called as combination of velocity triangle or combined blade velocity triangle diagram. Okay, this is diagram. Now, only thing is there that here in our diagram V2, this will be what? This is they have taken. There is problem. This will be V2. Okay, and this will be V1. आपण ह्या डायग्राम ह्या साइडने काढली त्यांनी त्या साइडने काढली. Here alpha 1. Here blade velocity is going to be U, A and B. If you consider this A and B, the blade velocity triangle. Okay, this is common for both triangle, inlet triangle as well outlet triangle. Inlet triangle म्हणजे suffix 1, V1, beta 1 to inlet. So alpha 1 इथे काय केलं त्यांनी blade the nozzle from the nozzle V1 is coming. Okay, instead of VA1 we should write this as VA V1. Okay, this is having two component. Other V1 बघितला तर ह्याचे दोन component आहेत. एक म्हणजे VF1 vertical आणि हा horizontal आहे तो VW1. ह्याला काय म्हणतो whirl component of steam at inlet. VF1 ला flow component of steam at inlet आणि alpha 1. आणि हे U आणि हा U इथपर्यंत A आणि B चा ABU आणि हा AC आहे तो E. यांच्यातला जो रिलेटिव्ह डिफरन्स आहे त्याला आपण काय म्हणतो VR1. ओके, अँड VR1 जो हॉरिझॉन्टलचा अँगल करेल त्याला आपण म्हणतो बीटा 1 आणि V1 जो हॉरिझॉन्टलचा अँगल करेल त्याला आपण म्हणतो अल्फा 1. हा ट्रायंगल आपला कंप्लीट झाला. नंतर आपण V1 चे दोन कंपाऊंड काढले, VF1 व्हर्टिकल आणि VW1 हॉरिझॉन्टल. हा झाला तुमचा इनलेट ट्रायंगल. दुसरा कुठला तुमचा आउटलेटला, आता इथून आपण VR2 रिलीज करतो आणि VR1 मेकिंग अँगल विथ द हॉरिझॉन्टल, इट इज कॉल्ड एज बीटा 1. इट इज कॉल्ड एज ब्लेड अँगल एट आउटलेट. आणि जिथून VR1 रिलीज होईल त्या पॉइंट वरून VR2 रिलीज होतो. आणि VR2 म्हणजे काय, ब्लेड व्हेलॉसिटी, रिलेटिव्ह व्हेलॉसिटी ऑफ स्टीम ऍट आउटलेट. आणि तो जो स्टीम हॉरिझॉन्टलचे अँगल करेल, टेंजेन्शियल डायरेक्शनचे अँगल करेल त्याला आपण म्हणतो बीटा 2. ओके, आणि यू आणि हा VR2 ज्याच्यामुळे डिफरन्स आहे तो कुठला V2. ओके, आणि मग हा जॉईन केल्यानंतर आपल्याला म्हणतो V2. V2 मेक्स अँगल विथ टेंजेन्शियल डायरेक्शन कॉल्ड एज अल्फा 2. नोझल अँगल ॲट आउटलेट, हा नोझल अँगल ॲट इनलेट. हा बीटा 1 म्हणजे ब्लेड अँगल ॲट इनलेट, ब्लेड अँगल ॲट आउटलेट. आणि ह्या V2 चे अगेन टू कंपोनंट, त्याला व्हर्टिकल आहे तो VF2 आणि हॉरिझॉन्टल आहे ते VW2. ह्याला काय म्हणायचं, कॉमन व्हेलॉसिटी डायग्राम. अंडरस्टँड? ही डायग्राम आपल्याला ड्रॉ करायची आहे, प्रत्येक न्यूमेरिकल साठी ड्रॉ करावं लागेल. अंडरस्टँड और नॉट? If yes, write down yes so that I can ask you to draw the diagram. Okay, now this diagram you have to draw, but consider that okay, I will ask you to draw this another diagram. Okay, so now this diagram you draw, because here ह्याच्यामध्ये आपल्यासारखे डायग्राम काढलेले आहे, फक्त V1. नाउ दिस डायग्राम विजिबल, यू ड्रॉ दिस डायग्राम इन युअर नोटबुक. अंडरस्टँड? डाऊट असेल तर विचारा. ही डायग्राम आपण फक्त काय केलेलं आहे, इथं फक्त आता ह्याच्यामध्ये आपल्याला थोडे फरक करावे लागतील. इथं फक्त VF1 म्हणा ह्याला फक्त VF2 म्हणा आपल्या नॉमिनक्लेचरमध्ये. Everybody, are you able to draw? Are you know the nomenclature? I am going to send all the PPTs to you, but still you have to draw the diagram. Anybody have problem, suggestion? Sir, repeat. Otherwise, yes, like Nikita Power told that she understood. Like this, you can write yes, 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 so that I can ask you to draw the diagram. Only VA1 च्या इथं काय करा, VF1 म्हणा. ह्याचा VA1 चा होरिझॉन्टल कंपाउंड VF1 आणि VA2 च्या ऐवजी VF2 म्हणा. बाकीच काय चेंज करू नका. Okay. So draw it so that now shall I stop now? Shall I stop today? Conclude lecture. This. Can I conclude today's lecture after taking attendance? If with your permission. Kunal, yes, okay. Viraj Patil, yes, okay. So I think this is the last lecture before Diwali. So I wish you happy Diwali, okay. And I will take attendance. But I will send all PPTs now. Yesterday I have forgotten. Condenser and turbines, okay. Nozzle, condenser and turbines. So that next week our ISC will start, and ISC 1 will be on the second section. Now this section, MCU type will take. And I will send the PPT. So okay. So give me attendance fast. Today is 10th. I think in Diwali vacation, I think I will miss one lecture. No problem. Okay, not roll number 1.
Present, sir. Roll number 1 present.
Roll number 1 present. 2. Okay, 2. Roll number 2.
Roll number 2 present, sir.
2.
Present, sir. Yes. Yes, sir.
2 present. Okay, roll number 2
Yes,
also
sir,
present.
present.
3. 3. 2 present. 3. Roll number 3. 2 present. 3 absent. 4. And don't write roll number. I am taking attendance. Only that particular person, if he is unable to give attendance, okay, then he can write that roll number. Okay. Roll number 4. Absent. 5.
Yes, sir.
Okay, 5 present. 6. 7. 8. 9.
Yes, sir.
9 present. Rahul. Okay. 10. 11. 11 might be present. 12. 13.
Yes, sir.
14. 15. 16. 17. 18.
Yes, sir. 18.
18. Okay. 19.
Yes, sir. 19 present, sir.
Okay. 20. 21. 22. 23. 24. 25. 26. 27. 28.
Present, sir.
Okay. 29. 28 present. 29. 30. 31.
Present, sir. 30 present,
30
sir.
present. 31. 30 I have taken. 31. 32. 33. 34.
Yes, sir.
34. 35, 34 present, 35,
35. Yes, sir.
35 also present, 36, 37, 38,
Present, sir.
39, 38 present, 39, 40,
40 present.
40 present, okay, 41, 42, 43, 44, 45,
45 present, sir.
45 present, okay, 46, 47, 48,
47. Yes, sir.
48 present,
47.
sir.
48 present, 47 present, 48 present, okay, 49, 50,
Present, sir. 50.
okay, 51, 50 present, 51, 52, 53,
Yes, sir.
53 present, okay, 54,
Yes, sir.
55, 56, 57, 58,
Yes, sir. 58 present.
58 present, 59,
59 present, sir.
okay, 60,
Present, sir.
61,
60.
Yes, sir. Present 61.
60 present,
present,
sir.
okay, 60 present, 61 present, 62, 63, 64, 65
65 present,
present,
sir.
66, 67,
57 present, sir.
67 present,
57 present.
67,
Yes, sir.
67 present, okay, 68,
Yes, sir. 68 present.
69,
Yes, 68, sir. Present.
70, 70 absent, 71, 72, 73, 74, 75, 76, 77,
78
78
present.
present. Okay, 69 also present. Okay, I have taken it.
68, sir. Hello, sir.
68 also I have
68.
taken attendance. Good. See, present. Okay.
Yes, sir. Yes,
So
sir.
shall we close today's lecture?
11 present, sir.
Huh? 11 present. Okay, I have taken. 35 present. Okay, shall I close today's lecture? So best happy Diwali to everybody.
Yes, sir.
And after Diwali, we are taking ISC 1, preferably on the chapter number 5, 6, and 7. I will send the PPTs of all here, so chapter number 6 and combined. This is steam turbine chapter, and we'll take to everybody. Till that, best good luck to everybody. Thank you.